Hello! Today the Bohiki team will be presenting the preliminary design review for the Bohiki mission. The agenda for today is to discuss our mission objective, the mission success criteria, the concepts of operations, the design of the lander and payload, and the schedule and budget for this mission.
Our mission objective is to provide insight on asteroid formation, mining opportunities, and asteroid deflection by examining the composition, mineralogy, and internal structure of arrows at different altitudes within a crater. What data do we need to answer all of our questions and declare success? Our first goal is to investigate the formation of S-type asteroids, and we will declare success when we obtain data for mineralogical characterization, regolith composition, surface roughness, texture, and topography. Our second goal is to investigate mining opportunities, and we will declare success when we obtain compositional and thermophysical characteristic data, like the emissivity and thermal inertia of arrows, which will give us insight on the type of environment that future machinery could be potentially exposed to. Our third goal is to investigate possibilities for asteroid deflection, and we will declare data when we obtain data for the internal structure of arrows, like its impact history and macro porosity. Lastly, we want to investigate presence of water or hydroxyl.
To ensure mission success, a detailed plan was developed as seen here. First, the launch date of the main spacecraft carrying Bohiki was chosen to be when Eros is closest to Earth. Data from the Skylife shows that happens around November 2025 to November 2026. Using the JPL Small Body Mission Design Tool, the orbit was calculated for a launch date of July 8th of 2025, arriving at Eros 225 days later. After launch, the mission is divided by 3 phases: landing, calibration, and experimentation. For the landing, the Bohiki rover will be released from the main spacecraft that will be going around 6 meters per second at 6 kilometers from the asteroid surface. The lander will have an entry angle of 5 degrees, and it will descend slowly in freefall at about 8.45 meters per second. It's expected that it will not result in a difficult landing given Eros' low gravitational acceleration. In case a harsh landing occurs, the lander is designed to withstand this impact. The landing site selected is in the edge of the Psyche crater. This location was chosen so Bohiki could perform the experiments at 3 different elevations, hence collecting data from different stages of the morphology of the surface. After touchdown, Bohiki will orient itself upright if needed using the moving mechanism. Once it is upright, Bohiki will begin its instrument calibration. After calibration is completed, it will survey the area with its camera and collect data with its radiometer and hyperspectral microscope. If everything is in order, Bohiki will proceed to the next experimentation site. Once Bohiki finishes the 3 planned set of measurements, what happens next depends on its condition and how much sunlight input is receiving at its location. If these 2 conditions are met favorably, the rover could be used to monitor the changes that occur on Eros' surface.
The rover is a cube shape consisting of 6 carbon fiber walls with aluminum 6061 frames on its vertices. The dimensions of the Bohiki rover will be of 49 by 49 by 49 centimeters. The total estimated mass of this design will be 13 more or less 1 kilogram. The shape and material were chosen after analyzing and comparing different designs. The decisions on the cube-shaped payload was based on its symmetry and simplicity. A symmetrical figure will have a more arranged space for each signed instrument, which are the main components of the rover due to their importance to the mission goals. The materials were chosen to ensure that the structural integrity would withstand launch, landing, and any obstacle as debris or falling. To ensure that the rover Bohiki will operate under the expected conditions, a series of studies were made. The objectives of the studies were to evaluate the performance characteristics of Bohiki in 3 different environments: launch, landing, and on-surface mission. The results gave positive safety margins and an overall description of structural behavior at the operational environment. Next, in the payload design, in the science systems, we use MARA, Micromega, and SIVA-P. For the communication systems, we use two EnduroSats, X-band single-element patch antennas. For the electronic systems, we have the GNC OPS and the electric boards that are BAE RAD Systems 7503U compact board. For the power systems, we have the 55AH high rate lithium ion cell model 32770 and the solar panels that are 30.7% next triple junction prime. And lastly, the motor systems with the oscillating mass.
MARO is a radiometer used in JAXA's mascot lander in the Hayabusa 2 mission. This instrument will measure the surface brightness temperature. By monitoring this parameter throughout an Oronian day, it will be possible to estimate the surface thermal inertia, roughness, and emissivity. This insight into the thermal physical properties of the asteroid will aid in having a better understanding of phenomena such as the Yarkovsky effect, something of vital importance to understand given its potential of changing an asteroid's orbital trajectory. It will also aid in assessing some of the risks posed to machinery and possible future mining operations, as they will have to contend with thermal interactions with the regolith.
Micromega is a near-infrared hyperspectral microscope, also used by the mascot lander from JAXA's Hayabusa 2 mission. Its function is to measure the reflecting spectra of the regolith sample. With this spectra, it is possible to characterize its chemical and mineral composition. Some of the compounds that may be detected include hydrated minerals, ice, organic compounds, iron oxides, and absorbed or confined water and hydroxyl.
The SIVA-P camera system was first implemented on the Rosetta mission on its Philia lander. It has a resolution of 1024p and autofocus capabilities. Its role in the mission is to provide surface and contest data, to let us know about any hazards present, to give us information about topography and position, regolith phenomena in low gravity. In other words, the behavior of regolith in low gravity.
The schedule for this mission was designed such that the launch date would make the travel time a minimum. The schedule is divided in six parts labeled Pre-A, A, B, C, and E. The phase Pre-A is the conceptual study or the proposal is submitted. During phase A, the preliminary analysis takes place. After this, phase B starts with the definition of the mission with documents such as the PDR and CDR. Phase C and D are the design and development stage, where the rover is designed with much more detail, assembled and tested. Lastly, in phase E, it is the operational phase, is when the rover is launched into space and arrives at the asteroid. The budget was of $45 million, but only $31 million were used. In the direct cost, 91% of the budget was used. The other 9% was used in a F&A cost. The total cost was 69%, with margin being of 30%.
In conclusion, the Coquille rover was designed to meet all requirements and provide a simple yet effective solution for the mission success criteria. This rover houses instruments that can give information on the chemical composition, mineralogy, and internal structure of Eros Psyche crater. Extrapolation of this data will help scientists to be one step closer to discovering the mysteries of the formation of our galaxy. Thank you for your time.